Hello, my name is Kourosh Arasteh, and I'm one of the instructors for the autonomous race car course. For the last 4 weeks, students have been working programming their cars to perform a variety of tasks, starting with some introductory tasks such as following lines and detecting objects, and building up to more advanced challenges, incorporating depth cameras and LiDAR to detect and interpret the environment around their cars. They've been performing all of these tasks in a rich simulation environment, which allows for complexity to challenge students to develop novel methods of navigating their tasks. Today, the students are going to be presenting to you 2 major accomplishments. First, teams have been doing research and exploring individual topics that they'll be telling you about today. And second, they've all been competing in time trials and a final Grand Prix race. Welcome, welcome one and all. Thank you for joining us here with the Autonomous Race Car course at BWSI. We've got a pretty packed schedule today with explore videos and spotlights from our international team as well. So we'll get started with our videos. That was one of our 2 teams based in Athens, Greece, Team MNMR. The next video is from the second team based in Greece, Team ONP1. Thanks so much to our teams in Greece for those very polished videos with pretty epic music in the background as well. Our next video is coming from our Japanese teams from the Aero Institute in Ibisu in Tokyo.
So we are the Japanese students in this course, and let's get started.
Hello, I'm Manami Sekiguchi. I'm Yurika Nakabayashi.
I'm Ryota Aoki.
I'm Sosuke Sawazaki.
I'm Rika Maruyama.
And I'm Oki Sugiyama.
Here is the agenda. First, development purpose. Second, introduction of machine and code. Third, our stress. Fourth, progress and conclusion during our project. Finally, future prospect. First, I will tell you why we joined this program. In fact, At first, I was interested in the project because I heard that MIT was involved and I wanted to create something using Python. But I have more reasons why I finally decided to participate. First, I was interested in how control self-driving cars. I didn't know much about this field, so I wondered how they were recognizing the road and avoiding obstacles. Second, I saw the Rosnia's version video on the internet, but the movement is very different, so I wanted to know what made the differences. Finally, I wondered how I could make a safe car. Next, I'm going to talk about the machine and code. On the left is a picture of the actual race car we made. At the very top, there is a blue round sensor called LiDAR for recognizing obstacles and display, and below there is a depth camera, system nano, and Arduino. We went through the following process to make this race car. Assemble the car, learn how to use the depth sensor and LiDAR, create the code, run the machine, and solve the problems, repeating trial and error. The functions of the machine are as follows. First, the car can drive on a defined line. Secondly, the car can avoid obstacles formed by the sensors and follow the directions of the arrow marker.
Next, for swap. We have two swaps. First, instruction by experienced in work instructors. They've attended this course in the past, and they've been watching Japanese students for years. Each of them have the skills needed for this course. Some of them have made it their profession. Second, an environment where we can help each other as one team. We use teams to create an environment where we can easily ask questions in Japanese. Also, since we all live close together, we can get together and assemble the machine. We can reduce mistakes.
Next, about the difficulties during development and the solutions. First, the movement of the car was different every time. Second, the code was complicated and we didn't have much time to write the code. Let's move on to the solution.
Okay, to solve this problem, we have created the following solutions. So for the first one, which is the unstable control of the vehicle, we've overcome this by utilizing PID controls. And also as the day passed on, we acquired more wisdom to manipulate it. At the end of this term, we could now move the machines automatically using camera, LiDAR, AR markers, which is a raison d'etre of this project. For the second issue, the difficulty of coding, we all had trouble with this. Therefore, we engaged this all together, including our instructors, to beg for help. And for the last solution, we made time in our daily lives. In Japanese school, the schedule of this project just meets with our school exam. So we all made a little time to move a step forward.
At last, I'm going to share our future prospects. Firstly, we learned two things through this project. To advise team members, we need to understand well. Also, if you have any questions, it is better to ask your team. Secondly, we have three things we couldn't do. We couldn't meet with members because of the COVID-19, so it became an individual work rather than a teamwork. Because of a team with similar backgrounds and values, only similar options and views came out. In addition to this, we didn't have enough knowledge of Python. Lastly, there are two future prospects. It is important to collaborate with developers from various backgrounds and carry out face-to-face development. Also, we want to learn the knowledge and technology to realize an autonomous car that can actually carry people. Thank you.
Thanks so much for our Japanese teams at the Arrows Institute for providing that overview of the challenges this year. Now I think we'll dive into our Explore projects. These were projects where students chose a topic of interest to them and researched this topic and how it related to the simulation environment or an advanced topic that they learned in the course. We're going to start with Team 1, which I think implemented Monaco. the RACECAR boys. Today we're going to be presenting Project Apex. This is our Explore project, and we got to independently choose what we wanted to work on. And all of us being interested in racing and Formula One, we decided to choose this. I'm Daniel. I'll let some of the other team members introduce themselves.
I'm Beaver.
I'm Double.
I'm Alexander.
So our fundamental idea for this project was we wanted to create a custom racetrack and model a Formula One car in the Unity simulation. Afterwards, we wanted to create an artificial intelligence driving software that would use a documentation lab to generate a racing line for the AI to follow as the race against thieves. The documentation lab measures and stores the corners and turns of the specific track, allowing the code to be adapted to different racetracks. The vehicle uses LiDAR to avoid collision and detect corner information by tracking the walls adjacent to the track. The car moves slowly through the documentation lab in order to gather detailed information about the track.
So one of the challenges we faced while creating the racing software was the LiDAR cannot see farther ahead and determine the bend of the road, meaning that the car cannot anticipate the direction of the corner until it's already entering the corner.
We also had a lot of difficulty and learning curve in Unity. So for all of us, we had never used Unity before, and we learned quite a lot of things. So we this was actually our second car model. We were using a McLaren model previously, and we eventually found this model. And after painstaking hours, we were able to separate the wheels from the model and merge them with so-called wheel colliders in Unity. And that's what allows the wheels to actually spin on the model and the front wheels to turn. There was a lot of other physics that we had to tune. So the wheel colliders have slip on them. So you have asymptotal slip and extremal slip, forward and sideways friction. So that's something that took a lot of tuning. And we actually ended up getting it pretty close to real Formula One car. So that if you floor the car, it'll just burn out. It doesn't have enough traction to go. And occasionally you can get it drifting. So those are just some of the things that we did to kind of more closely model an F1 car.
So for our approach for the racing software, the documentation lab provides the car with information about curvature and corner distance through vectors formed by the steering angle and distance traveled at the angle, which was calculated from speed times time. Then the racing code utilizes a state machine and alternates between different driving states based off of different track conditions. The car detects the corner and its apex by comparing adjacent frontal area LiDAR scans with each other. An abrupt difference in the LiDAR reading signifies an upcoming turn. After detecting a corner, the car would pair the corner with data gathered from the documentation lab and apply minimum curvature trajectory planning to the data to generate the most efficient racing line by minimizing the squared sum of the curvature values. The new trajectory allows the car to enter the corner from the opposite side and aim for the apex. This is a line commonly used by professional racing drivers. The ultimate goal of the software is to minimize wheel churn in order to maintain the highest corner speed. However, we weren't able to complete the racing function due to lack of time, but we had successfully created the documentation software, and the car has the full capability to map the racetrack. In the future, we will continue to complete this software and make sure our car races well.
In terms of real-world application for the software, our implementation is actually quite similar to how similar autonomous racing systems, such as RoboRace, actually operate. However, unlike RoboRace, we're only using LiDAR, while RoboRace tends to use more sensors like radar and AI cameras. Our car is capable of adjusting if necessary to a vehicle that's side by side, which makes it effective for real-life racing, as it's able to defend its position. In future implementations, these color cameras and computer vision could make our application work on more than strictly walled circuits, as it would allow us to detect curves and track limits using image processing. This would make our program applicable in a wider variety of race courses, not just ones that are specifically designed for our program. In addition, the use of a more advanced state system with passing and defending states would make our simulation more realistic, as it would be able to fight back more and push harder.
Yeah, and as for where we're going in the future, we've actually really happy with how this has turned out. We have a lot of features actually that we're still looking to implement in the software. We have good traction control and input slip control. We have a actual steering wheel inside the car that moves with the wheels. We're going to be implementing different camera views, engine sounds, as well as
a multiplayer mode where you can race against the AI. And overall, it's been really fun, really interesting, and I think we've all been really happy with how this turned out. And it's just really fun to play, honestly. Racing against the AI is a great time, and it's super cool to see the simulation software take on a different life. So yeah, I think that's all for our presentation. Thank you for your time, and we'll pass it off to another group. Thank you.
Thanks so much. Maybe we can open it up to some questions from the audience. And if you're not familiar, you can use the pane on the right side of this live stream in the Slido section to enter questions in the Q&A.
Yeah, so first question that we have is, what states does your car have, and is there a reverse or backup state for when there's a sharp turn?
So we have a straight line state, which is when the car doesn't detect any corner. This is essentially also acts as a backup state because we use a really robust wall following software. So the worst that can happen is the car fails to detect a corner and go into the best racing line. So because we feel like the wall following software is robust enough, we do not have a backup software because we don't think it's going to crash.
We also have a detection state for when we're doing documentation, which is our very first lap. That's implementing our straight line state and some of our other states, and it just keeps it, and it gathers data on the corners so the car knows when to turn.
Thank you. And then next question we have in the chat is, how does the LiDAR detect walls on the sides when there's no wall on the track?
Yeah, that's a good question. We've actually implemented basically the way our track works is it generates invisible walls alongside the track. And that's used, as you can see in the LiDAR, to map the track basically. And it's just a more robust way for the camera to understand what's going on really, because we don't have that information from just the color camera.
Thank you. And then next question is, how did the addition of the asymptote and extremum slip ultimately affect how you made your car turn?
Well, so the greater the extremum slip, the more force the tire can experience before it spins out. So that changes how fast the car can approach certain corners. And if you're moving too quickly, if the extremum slip is too low, the car will end up spinning out more often. And then the asymptotal slip is it's a little bit more different and more complicated. But making that lower kind of makes the car less grippy when it's spun out, and making that higher makes the car grip longer.
Yeah, it was really just finding the balance between grip in an F1 car and also, having some fun with the car, being able to drift. And I think we have the perfect balance where you can see the car spinning out if you just floor it. But as you get to the turns, you can actually kind of start drifting. So that just took a lot of tuning, but we have it in a pretty good state right now.
Thanks so much for those questions, and keep them coming. In the meantime, we'll move on to the next group, which is presenting Project CAVERN.
Autonomous Vehicle Exploration and Recursive Navigation, or CAVERN for short. The fundamental question that guided our project was simple: why collaborative autonomous vehicles? Let's take an example. In 2018, a Thai soccer team was trapped in the Tham Luang cave. This incident garnered widespread global media coverage. The issue that rescuers faced was that the cave was flooded and extraction would be incredibly difficult. It took a total of 18 days and 2 casualties before the team could be rescued.
In case an incident like the one described happens again, it would be much safer and more effective to deploy caverns. We could deploy a network of collaborative autonomous robots to explore the cave network. By coordinating the motion of these robots in a path planner, we can efficiently find the cave's exit, making us find the exit route quicker. This would also be safer as humans don't have to go to dangerous territory themselves. Our project idea was to make a search and rescue mission using autonomous robots that can communicate with each other.
In our project, we assume that a natural disaster has struck, and there are 2 main disaster areas with survivors in this complex environment. So the first one is this red high priority region, and the second one is the green low priority region. These white AR markers in the bottom row represent dead ends, and the white AR markers in the top half of this environment represent junctions in this binary tree structure. So the goal of the project is to use autonomous search and rescue agents to search through this maze until they find the high priority red region. And while they're doing this, they need to be able to avoid or reroute if they hit dead ends, such as these ones, and also if they reach low priority regions, because that's not as important as this red one over here.
Here's a demo of our project. You can see that there are two cars that each take a path. One of the cars takes the leftmost path, while the other is taking the rightmost path. You can also see that the rightmost car has found a green marker, which symbolizes a disaster area with low priority, and is currently waiting there. Meanwhile, the leftmost car found a dead end, symbolized by a white marker, and is backing up to try a new path. As the car continues to traverse the maze, it is keeping track of its exact position along the maze using a string of zeros and ones, which represent left and right turns respectively. Finally, once it has found a red marker, which symbolizes a disaster area with high priority, it stops there and sends its current position to the rightmost car. The rightmost car will leave its position at the low priority disaster area and use its position and the position sent to it by the other car to find the optimal path to the high priority disaster area, where it stops. Thank you for listening to our presentation on Project CAVERN, and we are happy to answer any questions.
All right, awesome. Thank you, Team Cavern. The first question is, were you able to have the cars communicate with each other to avoid collisions? And if not, how would you try to avoid collisions?
Yeah, I can take this question. In our current implementation, we haven't included anything that has these cars avoid a collision. So currently, they would just both get to that final red high priority point and just stop there. But yeah, I think in the future, that's definitely one path that we want to explore, where when they both come to that final position, one would park closer to the right side and maybe the other one to the left side, so that they can both, have enough space to actually proceed and do so without colliding.
Thank you. And then next question we have, how do you tell the other robot its position?
So while the car is traversing the maze, like I said in the video, it's keeping track of its position using zeros and ones to represent left and right turns. And when it reaches like a high priority disaster area, it tells the other car to come to it using that string in a TCP server. So both cars are connected to it before the program starts. And yeah, they're both listening throughout the program. And once one of them finds a high priority disaster area, it tells the other car using the TCP server. And yeah, the other car comes to the high priority disaster area.
Thank you. And the next question is, how does the second car calculate the most optimal path based off the location of the first car?
So basically, it's the path of the first car. If it reaches destination, it sends that path, and that path is composed of zeros and ones, and you can think of those as branches. So the car is going to look at that path and see where the path is different from its own path, and it's going to back up until it's at that node, and it's going to take the right direction, so it follows the right path.
Yeah, just wanted to add one thing. So the first car, you may have noticed that first it explored, a bunch of paths on the left side, and it hit some dead ends. And then eventually it found the correct path. And the path that it sends over to that second car is the optimal path. And that is the one without the dead ends. So as that second car is coming, it will already be following the most optimal path, and it won't make the same mistakes that the first car did. And that's where that collaboration comes in.
Thank you. And then next.
Yeah, we're going to keep those questions coming in the chat. In the meantime, we're going to move on to team 3, which implemented an autonomous Uber taxi.
This is our 2021 Summer Explore project on an autonomous Uber. So the original idea for our Explore project was to have an Uber-style program running in a city built within Unity. It would be a city similar to the real world where the race car would function as a fully autonomous car that could drive to a passenger, pick them up, and then drop them off at a specified destination. Here's an example of a basic grid style city. We wanted to design it after New York because it's a lot easier to navigate when the city is a grid. We didn't end up using this numbering system and instead opted to use the Python style numbering used in 2D arrays.
So these were our main goals. First, we needed to build a basic city in Unity so that we could test our code. Our second goal was to implement AR tags in Unity and interpret those in the code so that we could have a passenger location. Our third goal was to build navigation blocks in Unity and use those to tell the race car its location. And lastly, just like in real life, we wanted our car to stay to the right of the line on the road, but unfortunately, we weren't able to implement this because of the time constraint and because of the fact that the car needed to see the navigation blocks in a limited view. These were some of our stretch goals that we planned to accomplish if we had more time. So first, we wanted to add trees, sidewalks, and pedestrians to make our city more city-like. We also wanted to add functioning traffic lights and have the car obey them. And lastly, we wanted to make it look like the cone was an actual passenger and animate the passenger getting on and off of the car. Of these, we ended up being able to animate the passenger by making the cone come with the car once it touched the cone. In addition, we were able to implement the traffic lights in Unity.
So our entire city was built in Unity, and here are some pictures of our city built in Unity. We used red vertical lines and blue horizontal lines to allow the car to know the direction it's moving, and navigation cubes with different colors on each of the cube's faces to help the car know its location. There are also red and blue AR markers which the car can read to know the location of the passenger and the passenger's drop-off site. The black dots are our traffic lights, which change color from black to white. We were running out of different colors to use, so some of the realisticness of our city was lost. Some of our main challenges were not having a collaboration possibility. So as a result, I was the main person working in Unity, while everyone else was working on programming the autonomous vehicle. I also had no experience using Unity before, so I had to learn everything. I did a lot of research online and it was really helpful having the existing race car sim in Unity to work off of. I was also able to speak with Matthew, who helped me with some of the coding. And when coding the stoplights, I was fortunate that I already knew Java, which is really similar to C#. So I was able to implement a counter to switch the circles from black to white using the light renderer. And then passenger pickup was our biggest challenge. It was difficult to figure out where we were going to put the passenger or cone with a mustache smiley face on. And originally we thought about putting it on top of the car, but when I tried that, the LiDAR sensor was blocked. So eventually I was able to attach a capsule collider to the cone. So when the car came into contact with the cone became attached to the car and moved along with it to the final destination.
Regarding the Python portion of our project, we had three main goals: reading the AR tags and driving to its location, determining the car's position in the city, and implementing the traffic lights. We wrote a state to read in the AR tags with the IDs on the red and blue AR markers representing the X and Y values of the passenger respectively. Based on the IDs, we coded our car to autonomously drive to the passenger's location using line following. Using the colored navigation blocks at every intersection, we were able to get and update the location of the car at any given point. For example, if a car sees a purple block, it would increase its X position by 1. We also were able to complete our stretch goal of implementing traffic lights so that our car would continue driving when the light was black and would stop driving when the light was white. And here are some pictures of our Python program. And here is a video of our project.
So some of the real life applications that we can foresee use for of our program would be, for example, an autonomous taxi Uber system in which a user would be able to call an autonomously driven car to its own location and then direct the car to drive it to some alternate destination. Another example of a real life application of this program would be delivery services such as Amazon or Domino's Pizza, where the car would be able to drive itself to a location and drop off whatever it was carrying. The third real life application that we could foresee of this program would be something such as emergency services, like an ambulance, where potentially the driver is more needed assisting whoever the ambulance is driven to find. And so the ambulance would be able to autonomously drive itself to the location it needed to go to. That way everybody could help in the back assisting the victim. Thank you for watching our presentation.
All right, thank you so much. And then first question that we have is, what were the biggest challenges you encountered while connecting the new Unity sim to your RACECAR code?
There weren't that many challenges. It was pretty simple. We coded everything for our car in VS Code, and then we just we ran our code in Unity itself, and we were just able to run and connect like normal.
Thank you. And the next question is, would you be able to run multiple Uber programs at once? If so, would the cars be able to avoid colliding with each other?
As of yet, that's not something we've implemented. I suppose it's definitely possible to implement something like that. It would definitely require reworking some of the code and implementing a collision prevention. But I think if stoplights were sort of timed so that people going like in perpendicular directions didn't collide, that would be the best way to avoid a collision.
Thank you. And the next question is, does it know the shortest path that the Uber can take? And if so, how?
Yeah, so our Uber takes the shortest path. So it gets its current location and the location it needs to go to. And it first drives along the X direction until it reaches the X coordinate of the passenger or the destination. And then it drives along the Y axis until it reaches the coordinate of the passenger.
Thank you. And then next question is, have you considered adding a panic stop stay for real life pedestrians, animals, and cars?
That was actually one of our original ideas, to add like people walking in the streets, and then have the car detect them and not like hit them. But unfortunately, due to time constraints, we weren't able to implement that. But that's definitely something we would implement. Yeah.
Thank you.
So much. Next up, we have a project for the Explore City.
Hi, my name is Pippi, and my teammates are Lori and Anna. For our Explore project, we built a city simulation and coded our car to explore the city. Initially, we thought of making a three-dimensional maze with multiple floors which the car can navigate autonomously. Using the data from the LiDAR, when it arrives at the intersection, the car will make a random decision of left or right. We also attempt to implement model-based Q-learning to optimize the shortest route by awarding each correct decision. This approach was relatively successful. And then we decided to take our project to the next level. Instead of navigating through the maze, we built a whole city simulation in Unity from scratch. We then programmed the car to navigate the city by following traffic signs.
The goal of Explore City is for our race car to travel from the starting point, the garage, to the ending point, the gas station. This can be implemented in many different ways, the most simple of which is to follow the blue line until the purple turning guides are approached, guiding the car into the gas station and using the cones to know when to park.
The car relies on 3 sensors: the LiDAR, depth camera, and a color sensor. These sensors help the camera understand its immediate surroundings. Our program uses the color camera to navigate by recognizing different colors and their meanings. For example, the car knows to follow the blue line. The car knows to look out for red, such as the red in a stop sign. The car also knows to look out for other various street signs, such as the yellow turning signs. Our car knows to follow the blue line even with sharp 90-degree turns and then again stop at the stop signs. It looks out for signs at all times, even in unexpected areas. Then, the car begins to follow two parallel purple lines until it reaches the gas station. The car also stops at the orange cones.
The most challenging difficulty and limitation that we encountered were the limitations of the sensors. The LiDAR signals is barely useful due to the complex structure of the buildings compared to plain walls. The color camera is disturbed because there is similar red color in the bricks of the building. The depth image cannot pick up thin objects such as streetlights, palm trees, and traffic signs.
Due to the time constraints of this project, we have many other ideas for future improvements, the first of which involves signs. Currently, we recognize signs by registering their specific colors. However, this would not hold up in other environments, as, for example, the red on a stop sign could be found in many other places. A better way to implement this would be using computer vision, which would allow us to teach our code what each sign looks like, as seen in the image above. This can be done by feeding it many images of labeled signs in different contexts until it is able to recognize non-training images. Another interesting idea would be to allow the car access to a map so that it would have the information on every destination in the city. This way, the user could input a desired destination for the car.
All right, thank you so much, Team 4. First question that we have is, how did you resolve the color masking issue with the red stop sign and the red buildings?
The way we implement that is from actually putting a really narrow color range for example, the red stop sign. As you can see in the color camera, the red stop sign is a really bright red. And we actually face a lot of difficulties with that because initially the buildings are actually a much better red actually similar to the red stop sign. We have to make the building a less red building to actually implement the color camera to actually detect the stop sign. But because we can narrow the color range to a smaller range, the color camera is actually able to pick up the actual red sign to sense it to stop.
All right, thank you. And then next question is, do you have any ideas for a way for the RACECAR to follow directions and street signs without the use of colored lines?
We were thinking about using like the white dotted lines, but that was a little difficult because like they were dotted. But I think if we had more time to work on it and we were able to tune it more, we could probably get that working.
And also for future improvements, we can also, as we mentioned in the slides, we can implement computer vision to actually detect the actual sign, because in the real life, there's actually signs with the same color but mean different things. So another good Explorer path for us to do is to actually implementing computer vision, which will be something interesting to follow up.
Thank you. And the next question is there a reason why you switched from a blue line to a purple line to park at the end?
The reason we use different colors is for actually for more straightforward coding. As we detect the purple line, the car will enter a state which it will knows that it will actually start the parking state, so it will go into the gas station. But that's for sure that's not the real case in the real life. But for the purpose of simplicity, we use different colors.
Thank you.
So much. Our next project involves machine learning inside of the Unity simulation.
Hello everyone, my name is Austin Huang, and my group will present our project on machine learning in Unity. Our motivation for choosing reinforcement learning is that it is a hot topic in the field of AI and machine learning. We wanted to get a close look into how it worked and apply it to one of the significant challenges we faced in the RACECAR curriculum. This project also gave us an opportunity to explore various advanced features in Unity. Our objectives were to create an ML environment and train our race car to navigate through a cone slalom course. We used 4 stages for this training process. In the first stage, we had a simple straight line of 4 cones alternating between red and blue. In the second stage, we introduced the curved layout. In the third stage, we had a randomly curved layout to help the code in the car be more robust. And in the fourth stage, we tested it on the Phase 1 challenge course.
Hello, I'm Steven, and before we go deeper into what we actually did, let's explain some of the brief concepts and methods and tools that we used in our machine learning model. A big thing was reinforcement learning, and this is essentially, you can think of it as a free-for-all where we sort of let our robot just drive around and figure things out. And the way we make the robot learn is by feeding it rewards. So if we want to pass a blue cone, let's say to the left, we would give the robot a positive reward for that, and we would give it a negative reward if it does the undesirable thing, which is passing the blue cone to the right. And this ultimately helps the computer distinguish, what is something that we want to do, which is what is something we don't want to do. And the ultimate goal is to keep doing things that will lead to what we want to do, right? Now, on top of this reinforcement learning, we also use a neural net. And what a neural net basically does is that it takes in all the information that we collected to reach a certain action. And it does a bunch of mathematical calculations to give us a final action that we want to do. Basically, we have these weights, and we want to sort of emphasize actions that lead to a high reward, right? Because a high reward means that we're doing what we want. And ultimately, as more information is spoon-fed into the neural net learns that like certain weights are going to be emphasized and certain weights are going to be less emphasized, right? And ultimately, this allows the computer to understand information that's valuable versus information that's not valuable.
Hello, I'm Daniel, and I'm going to be explaining some critical decisions that we made regarding the implementation of our reinforcement learning project. First, I want to talk about ML agents, which is the framework that we used in order to train our actual model. So it's super important to our project. What exactly is ML agents? It's a package that allows you to communicate between Unity and Python, but more specifically, it allows you to control the decisions of a character in Unity, in which case we're doing a race car, and train it upon a Python neural network framework. We're using PyTorch. So this was just too perfect not to use, It's a very efficient, very pragmatic type of setup, and our simulator was actually built in Unity, so we just decided to stick with it. So now that we had a machine learning framework, all we had to do was run something on that machine learning framework. So we used something called PPO, Proximal Policy Optimization, which is a type of policy gradient which helps maps actions to states in a reinforcement learning scenario. PPO was already kind of pre-set up on ML agents, so all we had to do was actually run it and tune a lot of parameters, but once we got those parameters correct, it worked very well. It was efficient. It was easy to implement. It was good with continuous decision making, and it was very easy to tune. So overall, it was fantastic. We also used something called imitation and Gale learning, in which we would manually record a file of us running through the track, and then it would take that into account when it's training in order to kind of speed up the process, and it sped it up by quite a bit. And then finally, we used something called a curriculum style of training, in which we would train the model on an easy level, and then we would up the difficulty of the level, and then we would reset the learning rate, and then we would train it over and over, and then eventually we got to a rather difficult state. And so now we're going to be moving on to the results.
In our Unity environment, we started by using the color camera to train our model. However, after a few days of training, we realized that using the color camera wasn't the most efficient way to train. Instead, we started using RACECAR, which are a modified version of LiDAR that allows the machine learning model to have simplified data about distance and the type of object it's looking at. After the first day of training with the color camera, the model was able to successfully go through 4 cones and reach the end. However, when the cones were structured differently, such as a different distance apart, the model failed. Because of this, we switched to RACECAR, and the model was able to do much better, going through many cones with a randomized left and right and up-down value. This allowed the model to generalize the location of the cones to do better on conditions it hasn't seen before. On the 3rd and 4th day, the model kept training, and it was able to do curves in the cones. This allows it to go across bends like the one seen in the P1 challenge. By day 4, we were able to try our machine learning model with the P1 challenge. We were only able to get halfway with the current model because of some of the limitations with our training environment. This can be fixed with more training or with training specifically on the P1 challenge environment. At first, when training our model, it took a few 100,000 steps for the car to figure out a basic turn to go around the cone. After that, however, the car started learning much faster as it was able to generalize the steps for the other cones. We used the car's color camera at first, but realized that training took too long as the machine learning model had too much data to process. We switched to using RACECAR, and the training process became much quicker.
All right, thank you, Team 5. And the first question is, how do you think your program would have performed entirely organically without the help and direction it received from the imitation and Gale learning?
I can try to answer that first, and then Mel can add on. I'm not too sure about that because we had a time constraint, and as you know, training will take a long time. So imitation and Gale learning was kind of necessary to speed up the process. We were able to get through like the first day of just 4 cones in a straight line, and kind of the second day through just changing to RACECAR, but like it would have been really inefficient to train more without the imitation and Gale learning.
Yeah, just to add to that, we tried doing it without imitation learning on the longer courses, but we quickly realized that it was failing after we let it train for a couple million steps even, so it just really wasn't efficient.
All right, thank you. And next question is, do you think it's possible to generalize your model to work on any cone course without training to a specific one?
I can get this one. So basically we had just trained on like the 4 steps that we did, and we actually originally didn't train for the P1 course. We just put our model into it and let it run on its own.
Yeah, the P1 challenge actually presented some unique difficulties because we had trained it on a rather ungeneralized environment, right? We set up like a randomized position for the cone by day 2 and 3. But for P1 challenge, as you can see in the very end of the video, the raycasts are actually intercepting the slope downwards, right? So the data is actually changing for the model. But I think the model would work rather well for any randomized, generalized, flat, normal cone solving course.
All right, thank you. And the next question is, How long did the training take for each level?
So we did a bunch. So for our group, we did a bunch of training, like each level like parallel. So like some of us would be training one model at the very first day, and then some of us would be moving on. So I think it took us like a few million steps for each model. And based on how fast our computers were, that would be about around like 12 hours. So we would leave pretty much our computer running overnight to train. So for each level, that would be around like one day or one night, I would say.
Yeah.
To add a little. Oh, okay. Just to add on. At the end, our model was probably around 30 million steps, like in total. And a step is a decision, so the car decided a speed and angle about 30 million times, basically.
All right, awesome. Next question is, what steps did you take to figure out how to reward the race car for going in the correct direction?
There's hitboxes on each side of the cone, and so when it passes it, it kind of passes a reward signal to the car. That's pretty much it. But actually, to elaborate on that, with the model PPO, there's something called the gamma value. So you want to reward the car for doing something to get a reward faster, almost as if like you want to get money today, not like 10 days from now, right? It's better to get money now. So the gamma value makes the reward decrease over the time of the episode. And then what I was saying with the increasing the learning rate at each new lesson of the curriculum, like we reset the gamma value at the beginning of every time. So that's it.
All right, thank you. And then last question is, does your model predict that the cones are going to be alternating? Would it know if you put 2 red cones in a row to go in the right direction?
I could take this one. So the answer is yes, because our model knows the difference between red cones and blue cones since they're tagged differently in the Unity environment. And also the model knows to go into the checkpoint and not the failure hitbox. So that means if we had 2 red cones in a row, it would be able to generalize and go straight through them.
Thank you.
Thanks so much. Our next video is also using machine learning, specifically reinforcement learning for wall following.
So our project was to implement reinforcement learning. And we had a couple major goals, which was to navigate a set environment and without hitting obstacles and trying to optimize the movement as much as possible. So what is reinforcement learning? It is a branch of machine learning which trains an agent in an environment, and the agent is trying to maximize its reward. So it's going to learn by going through this environment over and over again. And with Q-learning, which is what we used, it maps different states, which we had LiDAR values and different actions, and then fills up a table with rewards based on those states and actions.
To implement this, we had a few challenges. The first was using the LiDAR. So we divided the LiDAR data into 6 subsections and then used those as binaries. So if an object was detected, it would be like a 1. If an object wasn't detected in that subsection, it would be a 0. And then we designed rewards to give rewards for correct actions and take them away for like crashing or other negative actions. And then we thought about implementing a reward based on distance traveled. So integrating the acceleration from the IMU to find the displacement, but that proved to be inconsistent.
To elaborate on the LiDAR challenges, the LiDAR originally gives a 360-degree reading of the entire car, but we only use the front half. And like Matthew said, we split it into 6 sections and each giving 1 or 0, depending on whether it detects something or it doesn't. If you see on the examples, on the first example, on the sides, there are only 2 walls. So it read 10001. And the second one, it was the walls right in front of it, but not on the right side. So 11000, and same for the next one.
Yeah, so now I'll talk about the reward system that Matthew touched on. We have 4 main ways of giving reward. So the first is if the car crashes, it gets -10 reward. This is the biggest penalty as we don't want the car crashing. We also give it anywhere from -3 to 3 reward for staying in the middle of the lane. And then we give it -2 for being too close to either the left or the right wall, because we want it far away from that. And then lastly, we give it anywhere from -4 to 4, depending on how much space is ahead of it, as we don't want it delaying its turns to the last second. And here's the code for how we do that.
So now for the Unity environment which the race car runs in, we decide to modify the Lab 4B course, since this is the most time efficient way of making a course. And what we did to the course was basically removing the fail on crash script and remove the checkpoint object, so it doesn't reset at a certain point, it resets at a starting point instead. And we added collision hitboxes around walls and obstacles, and so that allows the race car to reset on hit instead of fail on hit. That's pretty much it, and this is a course image.
Okay, so next was the update function, which is basically loops 60 times a second. And the main thing we did here was first we check the next state, the reward, based on the LiDAR data, and then we basically map that into our table to pick or to reset the reward. And then we choose an action based on the current state, based on what has the highest reward in the table. And then based on that action, we set the speed and angle.
And here's some demo videos of the car. So this first video here is after approximately 1 minute of training at the very start, and you see it constantly crashing into the left wall. And then you see it slowly figuring out how to turn properly. And then the second video is after 5 minutes of training, and you see it's finally figured out how to turn, and it's navigating the course. I'll just let it play out a little. Okay.
Yeah, so some improvements we would like to make if we were to do this again, or if we had a bit more time, was actually implementing that consistent reward system based on different distance traveled throughout the course. And then using more than 6 slices of LiDAR, so we could give a bit more proportionality to the angle turns. And that all factors into new methods of giving a reward, as well as using more accurate crash detection, perhaps through Unity rather than using the LiDAR. All right, and that's pretty much it. Thank you so much for watching.
All right, thank you so much, Team 6. And first question that we have is, did you make any adjustments to your reward system? And if not, do you see a way to make improvements to it?
Yeah, so originally we really only had a reward for staying in the center of the lane. But this kind of caused issues, especially when it was trying to make turns, because obviously there's not just 2 walls on both sides. So we had to add a reward, including like to map the front distance, which was just the 3rd and 4th slices of LiDAR data, and then use that to give a reward based on how far in front the wall was.
All right, thank you. And the next question is, do you believe that your code is generalized to the extent that the trained version of your car could run well on other courses with walls without practice on those courses?
Well, I would say not yet, because we ran into a few challenges, especially with the crash, because we had to base the crash on like a LiDAR reading. So whether like at any point the LiDAR was less than a certain distance, but this wasn't very consistent because sometimes it would just hug close to the wall. So it made it like pretty far after not that much training, but I think we would have to like add more rewards and other things in order for it to navigate like any wall course.
Thank you. And then do you think your algorithm would work well with uphill or downhill inclines?
Your mic isn't on.
Oh, hello? Okay. So I think it wouldn't work very well if we were going like up a steep hill because the front of our LiDAR would probably be triggered. And that like reward we were talking about where we give it a reward for keeping that front distance away, that would probably get really messed up going up a hill.
All right, thank you. And the next question is, what Python library did you use to train the model?
Well, we didn't really use like a library. We kind of like did it within the update function, and then we looked at some references like with other similar projects, but then we saved kind of the table which had which updates as the model trains, and we automatically save that into a text file. So then after training for a while, we could just take that and then run it in a different code, which was not like the training code, but instead just one for a trained model. So we didn't use like TensorFlow or something else. We kind of like just sort of wrote like our own algorithm. I don't know.
So like our model wasn't like a neural network, but rather just an array with all our reward values, and we just saved that in like a CSV file, which we use as our model for like the demo where we tried to drive the car around.
Thanks so much. Students also had an option to pursue a solo research project, and we have two of those today. The first is presented by Akhil Agarwal.
Hello, this is my presentation on my project on creating ice in the race car simulator, which I hope will help the developers create new and unique levels in the future. I first tried to create a physical material that would model ice with a lower friction. However, I realized that the simulator's race car uses its wheels' friction, not the friction of the ground below it. So instead, I decided to attach a script to any object made of ice that would change the friction of the race car's wheels. In order to create the ice material, I first created a script using Unity and attached it to the flat surface that would act as the floor. I used the script to decrease the friction of the race car's wheels when the flat surface was touching the race car. After creating the script, I added a new texture to the flat surface of the floor, causing it to look like ice. Finally, in order to create the Unity level, I used the demo level where I changed the ramp and floor to look and act like ice. You can see an image of the completed level here. Now it's time for a demo. As you can see, in this Unity level, I made the floor and ramp have the appearance and some of the properties of ice. First, the ice's low friction causes the car to slip, which leads to a very slow start when the car is initially trying to accelerate. You can also see that the car is much harder to control, since it slips often and continuously turns randomly. The car is also able to move much faster on ice after its initial acceleration. In addition, you can see that in very sharp turns at high speeds, the car skids and spins out of control until it comes to a stop. Finally, you can also see that the car continues to function normally on the material which most of the objects in the simulator are made of. Thank you for listening to my presentation about my project in creating ice in RACECAR Sim.
All right, thank you so much, Akhil. The first question that we have is, when the car touches the ice, is the adjustment applied to all of the wheels? So if only 1 to 2 wheels are on the ice, do the other wheels function normally?
Well, I haven't made that yet, but if I had more time, then I would probably make that but in Unity, when using the property that I was using, it already changes all of the wheels to have lower friction. You can't really control one of the wheels, so it kind of applies it to all of the wheels. It's touching those.
All right, thank you. And then next question is, what modification did you make on Unity to achieve the low friction environment?
Well, first off, I created a bounding box on top of the ice so that when the car is touching it, it can detect that collision and it can change the car to have low friction. And as for the part about making the low friction, it uses a value called like the friction extremum value, which basically changes the friction of the ice. So as I increase that value in the Unity C# scripts, then it basically makes it more slip. Makes it slip more, and yeah, I found kind of an optimal value for that, which made it seem like ice, but not also glitch out the simulator.
All right, thank you.
Thanks so much, Akhil. Our final presentation is being brought by Arjun Gupte.
Hi everyone, my name is Arjun Gupte and I'm part of the Autonomous Race Car course here at Beaver. And I will be talking about the project I've been working on for the past couple of weeks. It's called TRACK and it stands for Terrain Responsive Autonomous Car. First, let me introduce the main goal for this project. I wanted to integrate deep learning into the race car simulator we're using to enable the virtual car to drive autonomously on various terrains while adapting to their characteristics. This is very important because when driving autonomously, it's valuable to know what terrain you're driving on because that could help keep the car safe and also the passengers and the cargo inside of the car safe as well. But driving autonomously over unmarked and off-road terrain is much harder than doing so on well-marked terrain because there aren't any stop signs or traffic lights or reference points to use. So using a physics-based simulator to test such an off-road autonomous system is extremely helpful. So now let me talk about the approach I took to solving this problem. The first thing I did was build a visually realistic environment in Unity with all of the terrains that I wanted to test. Then I used a neural network to identify the terrain the car is driving on, and then based on the prediction, I adjusted the speed of the car appropriately. So if it's a rocky terrain and a bumpy one, I made the speed lower. But if it's a flatter terrain, then I made the speed higher. And then finally, I displayed the terrain predictions and also the adjusted speed values just to verify the results and their accuracy. Now, let me show a demo of the program. Okay, so I will be showing a quick demo of the program in action. Firstly, over here on the left side, you can see the Unity screen. You'll see the color camera over here, the main driver's perspective over here, and the label for the true speed. So this is what will be changing as the car traverses over different terrains. And over here on the right side, you'll see the CNN predictions for what terrain it thinks it's driving on, as well as what speed it thinks it should be driving on. So either low speed, moderate speed, or max speed. So now let me run the program. And you can see that first, it thinks it's on grass and it should go at a moderate speed. So this is a relatively moderate speed. But as it goes on to dirt, which it predicts over here, it says that the speed should decrease a little bit. So the speed starts going down. But however, as it goes back onto the grass and again back onto the dirt, the speed starts going down. It goes to 0.7, 0.75, 0.74 maybe. But as it goes back onto the grass, which it predicts here, the speed goes back up because grass is easier to drive on than dirt. Now, as it goes onto the asphalt, you can see that the speed increases, and the CNN is correctly predicting that it's on asphalt. And it also says that it's smooth terrain and it should go at max speed. So that's why you can see that the true speed here is a pretty high value at 1.34. But now, as the car goes back to traveling over grass, you see that the speed decreases because it's moderate speed. And the speed is now down to 1.03, 1.01. Now the car is going to drive over a rocky surface. And in this terrain, you can see that the speed drops to 0.4, 0.3. And that's because this is a very uneven terrain and it should go at a low speed. So the CNN is predicting it correctly, and it even drops the speed down to 0.1 and 0.2. So for this portion, it will continue driving at this low speed while it still is correctly predicting the terrain. And it will continue this until it starts seeing the next terrain, which is the grass. So we're still at a relatively low speed over here, which is correct. But now as it starts seeing the grass, which the CNN identifies, and now asphalt, you can notice that the speed increases again, all the way back up to 1.1 and coming up to 1.2. And that's corresponding with this current statement that says it's smooth terrain and we should be going at a max speed. Now, as it goes up the bridge, it continues identifying asphalt and it continues driving forward at a max speed. The AR tag that's coming up over here will indicate that it's at the end of the course, and you can see the speed starts decreasing as the car comes to the finish line and finishes its journey. Okay. Okay, so you saw the demo, you saw the car complete the track, and you saw the CNN make terrain predictions, and you also saw the car adjust its speed based on those predictions. Now I'm going to break down that demo, but first I'm going to focus on the Unity and the environment aspect of it. So Unity is a really nice tool to simulate this environment because of all of the realistic visuals, and this helps make the neural network training and inferencing a lot more accurate. Unity also has a lot of free assets. You may have noticed the mountain, the trees, the bridge, all of those things were free assets that I imported to make the environment look more realistic. I also did a lot of 3D modeling and painting of textures to make the terrain again look natural and realistic. The other thing is you might have noticed the red lines that the car was following weren't connected to each other always, and they may have looked like they were floating above each other. And that's because of the way the red lines are made, it's hard to get them to match the curving contours of the terrain. And because of that, it gives that effect of floating and not being matched up properly. But in the future, that's an enhancement I intend to make and fix. Another couple of modifications I made to the car include adjusting the main camera, so it's at the driver's perspective. And I also adjusted the wheels and the suspension to make it a little bit more tuned for off-road driving. Now, let me go into the deep learning part of this race car simulation. I used the ResNet 18 CNN model as the base neural network architecture. For the training portion, I built 4 main patches, and each one of those patches corresponded to the different terrains that I used. So asphalt, grass, dirt, and rocky. I manually drove the car over each of these patches corresponding to each terrain and collected roughly 150 images for each one of these categories. I then trained the ResNet 18 network, and then I tested it. I tested it on that track that you saw in the demo, drove it around that track on each individual terrain, and collected roughly 50 to 70 images so I could test the model. Then I analyzed the performance of this trained CNN, and we can take a look at the performance over here. For the training loss versus the number of epochs, I trained the model for 30 epochs, and you can see how the loss decreases as the number of epochs increases. For the test accuracy, this is actually in batches. So eventually the test accuracy rises up to 90, but then eventually stables out and bounces out to roughly 88%. And that was the overall testing accuracy for the model. On the right side, you can also see this confusion matrix, which has the predicted label, so the CNN's prediction on the horizontal axis, And on the vertical axis, you can see the true label, which is the correct terrain. And you can see that the numbers on the diagonal are extremely high relative to the ones not on the diagonal. So that means, for the most part, the model was able to correctly predict each category of terrain. Now, the last part I want to talk about in terms of the demo is the navigation. So after I uploaded the final tested and trained CNN to the RACECAR simulator, I wrote some code to actually print out those terrain predictions roughly every second. And then I also established some ranges, speed ranges for each terrain. And once the terrain is, let's say, measured at a rocky value, the speed that it would generate would fall within that safe range. I used, as I mentioned previously, I used the red line contour following to guide the car around the track. And I adjusted the speed based on the prediction from the CNN. And then I displayed these two things just so it's easy to verify the results, as I mentioned earlier. Now, in terms of the future steps that I want to take, there are a couple of things I want to try. The first and most important one is implementing the CNN on my 1/10 scale RC car using a Jetson Nano and driving that around on dirt, grass, asphalt surfaces around my neighborhood, so I can see how training in a simulator translates to performance in real life. I also want to improve the track in Unity and also the navigation algorithm by adding forks in the road so that one side of the fork has one terrain, another side of the fork has the other terrain, and the car should be able to predict the terrain on both sides, figure out which one is more drivable or which one is safer to drive on, and pick that terrain and choose that side of the road. I also want to try to make the environment a little bit more realistic, add a time of day and also some weather effects, just to make it seem a little bit more natural. And finally, I would like to thank Kourosh and Alina.
Arjun, unfortunately, we're running really short on time, so we're not going to be able to run over or have many questions. But thanks again for joining us. Thanks to all the students, and congratulations on completing a very difficult course. And we'll see you back in the main session for our final Grand Prix race.